So you all have to accept now to continue in the meeting?
Yeah.
So Janine, whenever you want.
Okay. So it's time. So for this flash talk session, the first speaker is Guido Masella from University of Strasbourg. So Guido, good luck with the 5 minutes for your 2 slides. You tell me when I need to switch slides, okay? Don't forget.
Okay, thank you. I hope you can hear me.
Yes, fine.
So good afternoon, everyone. And first of all, I would like to thank the organizers of the conference and of the mini colloquium. And sorry. And I am Guido Masella, and I am a postdoc in the group of Professor Guido Pupillo at University of Strasbourg. So here in this flash talk, I would like to summarize briefly the results of the pre-recorded talk that many of you may probably already saw. And a key point in the understanding of the transport and thermalization phenomena in a physical system is the understanding of the interplay between disorder and the interactions in many body systems. It is known that non-interacting systems undergo for high disorder strength to Anderson localization and thence to the absence of diffusion. A similar phenomenon it's also present for many body systems in the presence of interactions, and it's known as many body localization. And a striking feature of this kind of systems that undergo to many body localization is the fact that they fail to reach thermal equilibrium. While this phenomenon has been studied extensively in the case of local and short-range interaction, here we are interested in long-range interaction, and in particular in the case where interaction strengths scale as a power law of the interparticle distance, as shown here in the top right of the slides. This case is very important, fundamentally important in a plethora of systems, of physical systems. And in the case of a spin system with power law interactions in one dimension, the phenomenon of many body localization has already been predicted, and it has also been predicted that there is a critical power for which for the phenomenon to occur, a critical power of the interaction, and it is 2 in the case of the, for example, of an XXZ spin model, and 3.5 in the case of, for example, XY spin model. In the pre-recorded talk and here, I'm interested in the study of the following Hamiltonian, shown here in the bottom part of the slide, which is for hardcore bosonic particles on a one-dimensional lattice. And we study it via exact diagonalization methods, looking both at the level statistics and at the entanglement entropy growth in the system. So we have here a power law hopping between of particles between sites with power A, power law two-body interaction between particles with power B, and uncorrelated uniform disorder of strength W. And it is important to note that this Hamiltonian maps exactly into a XY model of spin, or an XXZ model of spin in the case of, in the first case, B equals 0, or in the XXZ model, A equal B, and in the case of A equal infinity, into an extended upper model with power law two-body interactions.
1 minute.
And thank you. In the next slide, I show you the phase diagram of the Hamiltonian for different models, and in the XY, XZ, and the extended Bose-Hubbard model. And as you can see in the three figures on the top, we have both many body localization and regime and delocalized regime in the three systems. But what we found, looking also at the slide, at the figure on the bottom, is that entanglement entropy grows algebraically with the time in these systems. And also we found, this is our most interesting result, surprisingly, that the power is universal at criticality. At the many-body transition, this power is criticality, and this has very deep consequences for the study of this system. For example, one can study one of the system at a power, for example, A equal 3, and then know everything about the transition for all the other powers. So I don't know if there are. I finished my time.
Just in time. 2 seconds over. So thank you very much.
I speed up at the end.
That's it. That's good. That's good. No, it's a difficult exercise. At least we know.
So I don't know if there are questions already, or.
Yes, or maybe the questions should be asked directly in the meeting rooms. Mariela?
Okay.
Yeah, we can do maybe a general round after all the talks,
Yes,
so that
yes.
we go one
So
after
that
the
we
other.
move
And
forward
then
now. Yes.
we
Yes.
see, yeah.
Let me go. Yes, here. So now Celia González from Madrid.
Okay.
You're there? Okay, so
I'm here.
Let me.
Okay, perfect. So good afternoon, everyone. My name is Celia González. I'm a master's student at Universidad Autónoma de Madrid in Spain. And today I will present our work in the development of nano-devices based on Fourier transition method dichalcogenides. Can you move next, please? Thank you. The discovery of the magic angle in twist bilayer graphene in 2018 has led to an increasing interest in the study of flat band properties and correlation effects in 2D systems. These systems provide a new platform for studying exotic quantum phenomena such as multi-insulaton transition and conventional superconductivity and ferromagnetism, among others. To date, these characteristics have been mainly observed in graphene Moiré lattices. However, transition metal dichalcogenides have a very similar geometry to graphene, and they are also potential candidates for fabricating and exploring the properties of these 2D twisted structures due to the lack of inversion symmetry and strong spin-orbit coupling. Here we take the first steps towards the fabrication of high-quality devices based on 2D transition metal dichalcogenides and the development of the technology for studying these systems. More information about our fabrication process can be found on my poster. However, I will say that we use the Scotch tape method for the exfoliation and all dry transfer with a polymer for stacking the flakes. In figure B, you can see an optical microscope image of one of our devices in real life. And we wanted to understand the behavior and basic properties of these crystals in order to be able to fabricate more complex structures in a near future, hopefully Moiré structures. For this reason, we used a basic MOSFET geometry as the one you can see in figure C, with top and bottom gates aiming to realize either a QPC on the left side of figure D or a quantum dot in the right side of the same figure. On the other hand, we wanted to check whether the gates design we were using for our experiments was suitable or not for confining a double or a single quantum dot. And for this reason, we have performed some simulations of our devices with console multiphysics. And in figure E, you can see one of the several gates patterns that we have used for our simulations. Can you move next, please? Thank you. Experimentally, we have studied the effects of thermal annealing, boron nitride encapsulation, and few layer graphite contacts on molybdenum disulfide devices. With these improvements, we lowered the contact resistance as well as we increased both the field effect mobility and the ion-ion ratios. In figure A, you can see the comparison between 3 different devices with different features. We got functional devices even at low temperatures. For us here, low temperatures means 8 Kelvin, with bottom gates working, as you can see in figure B, and we avoided a behavior with switches. Regarding the simulations, firstly, we could obtain a dot, although its size was maybe too large for access the quantization of the energy levels. In this case, the radius was approximately 300 nanometers. And after some modifications, we achieved a configuration where we could confine a large quantum dot that could evolve into 2 individual quantum dots by changing the gate voltage, and the radius of both individual dots was approximately 50 to 60 nanometers, so it's suitable for quantum confinement. Can you move next? Thank you. We have also studied the transport features in tungsten diselenide devices. We annealed them and we encapsulated them with boron nitride. And even though we couldn't measure them at low temperatures, we observed the ambipolar behavior at room temperatures, with different mobilities for electrons and holes, as can be seen in figure A in the red region and the blue region. And regarding the simulations here, we use the same gates pattern as before.
1 minute.
Okay, and again, we could confine a large single quantum dot that can be tuned into 2 individual dots with the same radius as before. And this is probably one of the first examples of this kind of simulations for these devices in literature. So this is a good starting point for the experimental fabrication of these kind of systems. Can you move next? Thank you. And as next steps, we aim to further optimize the contact resistance and develop local gate electrodes for studying the electronic properties of these 2D transition metal dichalcogenides based devices at low temperatures. Thank you for your attention. And if you have any question, especially regarding to the simulations, because that part is not in the poster, I have prepared some slides, so please feel free to ask. And thank you so much.
Thank you, Celia. So this was very clear presentation. So rendezvous for everyone in the meeting room to visit your poster. So our next speaker is Mikhail, and I must admit, Mikhail, that I didn't look at your affiliation, so I hope you give it in the beginning of your talk. Yes, Rostov.
Hello.
Okay, so you're welcome to start when you want.
Okay. Hello, my name is Mikhail Mayorov. I'm a student of Southern Federal University in Russia. Dear participants and organizers of the conference, I'm pleased to present here the results of our study of a perovskite compound barium ferrostenate BFS. This perovskite is oxygen deficient due to not isovalent substitution, and iron atoms partially have tetrahedral oxygen coordination along with octahedral one, which is typical of transition metals in perovskite. The electric and magnetic properties of these materials makes it attractive for electronic applications and also exhibits a photocatalytic activity. We explored the question of whether the local structure of the compounds depend of synthesis conditions and oxidative calcining. Thus, we have prepared 4 BFS samples using different regions, and half of the samples has been additionally calcined in the oxygen flow. Then we studied the local ferrum environment in all the obtained samples by X-ray absorption spectroscopy. We analyzed the pre-H intensities and the ferrum KH spectra of the samples and compared them to those of reference compounds in order to evaluate the average coordination number of ferrum atoms. We also performed exact study in order to get an information about radial distribution of oxygen atoms around ferrum. Based on the obtained data, the fraction of tetrahedrally coordinated ferrum atoms has been estimated for all the studied samples and appeared to vary from 30 up to 45%. In BFS, it was noticeably larger than in strontium ferrostanate. However, the difference between BFS samples wasn't that strong. The results of these investigations are briefly reported in our poster presentation, which you can find in the conference site. Thank you for your attention.
Thank you, Mikhail. So we have now Victoria. Victoria, are you there? Can you hear me?
Yeah.
Okay. So from the same institute.
Oh, I'm not sure then. Well, shall I demonstrate my screen?
No, I have it. I'm projecting your screen. So you tell me when you want me to switch slides.
Okay.
Okay?
Okay.
You can see my screen. Okay, it's your slide on my screen.
Yeah. Yeah.
Okay, good.
That's it.
Let's start then.
Thank you. Dear colleagues, I'm grateful to organizers of the conference for this nice opportunity to report the results of our study of the sodium titanate, sodium niobate system. This is one of the prospective environmentally friendly materials which is now widely considered for various electronic applications. This perovskite system has a very rich phase transition diagram, and not all of the phases and phase transitions has been properly characterized so far. Tantalum-rich compositions are known to exhibit a diffuse dielectric permittivity maximum at low temperatures. And this is why we decided to look more attentively at the composition with X at about 0.6. Two different methods has been used in our study. The phase transitions were examined using optical birefringence imaging, and thus the temperature dependence of birefringence and the orientation of the optical indicatrix all over the studied crystal had been obtained. Three temperature phase transitions have been clearly detected. The low temperature one has a second order character, and it is obviously responsible for dielectric behavior at low temperatures for this compound. We also studied the local structure of this compound using niobium KH absorption fine spectroscopy, and revealed that niobium atoms are located much closer to octahedral centers comparative to the pure sodium niobate. Some more details of our study you can find in our poster presentation. which is located at the conference site. Thank you very much for your interest.
Thank you. Thanks a lot. So we had the last talk from Alejandro Vidal from Madrid.
Hello, can you hear me?
There, okay. There you are.
So good afternoon, everyone. Can you hear me?
Yes.
Sorry or
yes,
not?
yes. No,
Okay,
it's
okay.
clear. It's
Fine,
clear. Your
fine.
voice is clear.
Hello, everyone. My name is Alejandro Vidal. I work as a research assistant at the Institute of Micro and Nanotechnology of Madrid, which is a small research center of CSIC institution in Tres Cantos. And I am part of the nanophotonics group, where we have several research lines, but today I'm going to talk about a recent approach we are following on nanoplasmonic structures for enhanced fluorescence. Yeah, thank you. So these nanoplasmonic structures are meant to amplify light thanks to a phenomenon known as localized surface plasmon resonance, which is originated when surface free charges interact with an electromagnetic field. And a couple of years ago, a group in South Korea demonstrated that a twofold increase in fluorescent intensity can be reached with substrates made of a gold silver alloy in form of nano islands. So in this presentation, I will introduce similar results that we got with a simpler two-step method of fabrication using just gold. So these gold nanoparticles were deposited on top of a glass substrate using an electron beam metal evaporator, which give rise to nano island-like particles, as you can see in that electron microscopy image in the slide. And on top of the gold layer, a COX spacing layer was added using a plasma-enhanced chemical vapor deposition. So next slide, please. Thank you. So we produce substrates with these combinations of gold and COX thicknesses that you can see in the top left corner. And fluorescent intensity assessment was performed at the confocal microscopy unit of CENIO Center in Madrid, that collaborated with us, by using fluorescent beads like the ones you can see in the picture, in that black picture, has fluorescent beads. And as you can see in the first graph, almost all substrates show an increase of fluorescent intensity as compared to the control, that is the first blue bar, with gains of even over 200% in substrate 3, for example. However, we are not yet able to see a clear correlation between gold and COX thicknesses and the final gain in intensity, because results show a great disparity. And we perform also a transmission intensity assessment with an ellipsometer of these substrates for all wavelengths. And as you can see in the second graph, there is a peak in substrate transmission at around 500 nanometers wavelength, which exactly corresponds to the fluorescent emission wavelength of the beads we are using. And that's what maybe explains that these substrates are suitable for amplification in this case. So in conclusion, we have developed a cheaper and simpler method for the fabrication of these nano island nanoplasmonic substrates, with up to a twofold increase of fluorescent intensity. However, it's true that there is still work to do in order to clarify the driving conditions behind these results. So thank you for your attention.
Thank you. So, okay, so I stop sharing. All the presentations have been done. So I guess now you will have been affected to some meeting room. Masella, are you there?
Yes.
Masella is our guardian angel. So
I tried, but yeah, that's why I don't know if we can have, if someone has like an urgent question now, or the other way we plan to do this is we have created these breakout rooms. You will see it in a second. So all the speakers will go to their corresponding room that you will find by their name. And then we will try to assign everyone to what we call the distribution room. So it's a general room. And where you will see in your, I will open the room so then you can already see. At the bottom of your screen, you should see a tab that says breakout rooms. And I will be assigning people, as I said, to the general room. And then inside there, you can see all the, when you click on these breakout rooms, you will see all the options where you can go, right? So you just move around. If you want to leave a breakout room, you will be taken back to this main meeting, or you can go directly to the different rooms inside this tab, okay? I don't know if it's clear, maybe it sounds very confusing, but I think once you see it, then it's very easy.
It's easier to do it than to explain it.
Yes, yes. So I will assign, as I say, everyone to the distribution room. And once you click and you're assigned, you will be able to enter there. I think I did it. People are disappearing, but I hope that they're going to the room and not to the... Maybe we go there to the distribution room as well. Okay, so who's here? Alejandro, for instance, you can go to, can you enter your room now? Yeah.
Alex is remarkably quiet.
Can you send me again the invitation, please?
You should receive it. I mean, you should look now below your screen. Are you using your mobile phone or are you using?
No, desktop. Yeah.
Desktop, okay. So then at the bottom of the Zoom meeting, you should see a tab that is called breakout rooms.